I would like to introduce you to a friend of mine, p-value. Since 1900, p-value has helped guide us in deciding whether our results are meaningful and has been the gold standard of statistical significance. But over time, people have misinterpreted small p-values, and people have misinterpreted large p-values. In fact, people have begun to misuse small p-values and large p-values. And this has led to revolt. As Alan mentioned, journals are banning the use of hypothesis testing and p-values. But I'm here to say, it's not your fault. All you promised was helping us determine what could plausibly be explained by chance, whether our data were consistent with a statistical model. And for that, you have done your job well. It is us that needs to do better. Do I think we can do better? Can we teach college, high school, middle school students to think inferentially? I think we can. I think you're going to see a lot of great examples this weekend of new pedagogies and new technologies that are making a difference. For example, simulation-based inference. Having students count candies, spin spinners, simulate tossing coins, constructing their own null distribution, I think does help them visualize and put their hands on that process and really understand that nebulous null distribution, really help them make those decisions in a kind of more efficient manner so that they can focus on the entire scientific process from beginning to end as a whole rather than disparate pieces. What is my evidence? Well, let me ask you this. Have you ever had a student come to your office hours the last week of the class, diligently studying for the final, proud that they found the right p-value, and then asking you, now what? What am I supposed to do with this? I don't remember. Is it large or small? What do I do? So maybe convincing you that they didn't quite get the big picture of the course that you had hoped. I can say that in my courses, that particular question has largely gone away. I can say based on data from thousands of students over the last 5 years, that particular question has largely gone away by the end of the course, at least compared to some historical averages. I can also say we're doing a better job helping students identify a correct interpretation of a p-value. We have a long way to go, but I think there's hope. Better yet, students now have new techniques and new directions that they can go, new questions they can ask. As a student asked you, I thought you told me the median was better than mean. Why did we stop talking about the median? Can't I get a p-value for the median? Yes, you can. Have they asked you, why did you stop talking about the distinction between random assignment and random sampling? Does that make a difference in how I assess my evidence? Well, let's simulate some regression lines under random assignment and under random sampling, and you tell me why those pictures look a little bit different and what the implications are. But we can't stop there. We need to reinforce and build on these ideas throughout all their introductory statistics and through subsequent courses for both statistics majors and non-majors. So instead of fighting over whose method is better than whose, instead of letting the p-value be the sole judge of significance, we need to look at all the clues. We need to work together. After all, a lot of our considerations on whether we have good data and good data presentation are the same. And a lot of our considerations on whether we have good methods are the same. So we can focus on those big ideas and have pillars that work together to get through that gate of wisdom, and possibly with multiple paths. So I think we need to support each other and learn from each other. And I think we need to learn from other disciplines and how they might be able to help us improve our own discipline. Thank you.
Next up is Danny Kaplan from Macalester. Let me get the technology working. Danny starts with a D. With the clicker.
Thank you.
This?
Which is the clicker?
To the right?
To the right.
To the right?
To the right. Hi, it's important that I speak loud enough that you can hear me. Is that the case? All right. Well, my title, as you can see, is a quote from Julius Caesar. And I was inspired to use a literary source by a sentence in the TAS editorial that Alan described earlier this evening, just a few minutes ago. The sentence is, "The tool has become the tyrant." And in Julius Caesar, Cassius and Brutus are conspiring to take down the tyrant of Rome, Julius Caesar. And in the American Statistician paper, the tyrant is statistical significance. About 3 years ago, as Alan pointed out, the TAS the ASA issued a statement on statistical significance. In this article, they elaborate on that, and I'll just read you a little bit. The ASA statement on p-values and statistical significance stopped just short of recommending that declarations of statistical significance be abandoned. We take that step here. Now, as Dennis Pearl will appreciate, I think, there's even a cartoon. And in the cartoon, a kind of stunned scientist is on the threshold of putting the tome of statistical significance into the rubbish of scientific history. Now, this cartoon wasn't in the American Statistician, it was in Nature. And Nature went on to describe in more detail their concern. And it turns out that their concern is that scientists, even scientists who publish in Nature, are making the fallacy of accepting the null hypothesis. And this has consequences for how science is being done. I think accepting the null is a serious mistake, but I think there are more fundamental reasons why statisticians are losing confidence in confidence. And I've got a few of them, I list a few of them here. So in TAS, there are many suggestions for how to fix things, and I list a few of them here. And in the spirit of an after-dinner talk, I'd like to add in my own proposal. I propose that we replace the stars, so often used in statistical reports, with the stars as they're used on Amazon.com. The graphics in Amazon stars remind you what's missing. You see the unfilled slots for stars. In statistics, 3 stars convince many people to accept a paper's conclusion. But as you all know, on Amazon, 3 stars points to a problem. Whatever be the article that's being sold, you're not going to buy it. I propose to use these stars as a kind of checklist for meaningful statistical practice. So on my scale, 1 star means that the confidence interval is not above 0, but above the smallest effect worth talking about, and that you should say, in terms of the science that you're doing, what that effect is. 2 stars is for incorporating covariates appropriately into your analysis, and that includes issues of causation and things like directed acyclic graphs. 3 stars, an effect size is large enough to have a practical benefit in everyday terms. 4 stars is that you've done an experiment. But in many matters of importance, it's impossible to do an experiment. So I've invented something called the confounding interval, which expresses the uncertainty created by unhandled or unknown covariates. And finally, the 5th star is that your finding has been independently confirmed. Going back to that editorial in the March TAS issue, the authors recognize that change is hard. And you can see they say, it's going to take work. It's going to take time. And notice they give a shout out to us here in this room. Right? We are excited that the U.S. Conference on Teaching Statistics will focus its 2019 meeting on teaching inference. So let's get started on this work in the next 2 days. If it's going to happen, it's because us here in this room are going to make it happen. Thank you.
Thanks very much, Danny. Next up is Hollylynne Stohl from NC State, who's also a proud Penn State alum, I recently realized. So let me find Hollylynne's slides.
Hello? Yeah, okay. All right, so I stood up during that time where it was about statistics education research, and I particularly focus at the 6-12 grade level. So I'm here to kind of talk about data science education in that grade level and talk about what shoulda, coulda, woulda, but ain't in the classrooms. So let's evaluate the evidence there. So shoulda means to show obligation. Coulda is to suggest a possibility. Woulda is to suggest the conditions under which, but ain't is to state what is not. So shoulda, we have an obligation to prepare data literate citizens, inspire the use of data for good, and motivate those future studies in data intensive careers. We shoulda because it's in the curriculum and not just in our math and statistics curriculum. I encourage you to look across the different domains. If you look carefully at the science curriculum, of the literacy curriculum, of the social sciences curriculum, of course in the mathematics and computational thinking standards, we have lots of different opportunities to integrate more data science activities. And I did an interview study with data scientists this past year and asked them at the end of the interview, what would you like to see in secondary classrooms to give students an experience of what a career in data science might look like? Well, yes, they think that computer programming and statistics are important things to learn, but they more talked about these opportunities to develop creativity and resilience in doing problems and attacking them with data, that they want that to be more of the focus. So yes, as Alan mentioned, we have a great interest in AP statistics and in computer science. We've got great possibilities that could be there. Computational thinking and coding is in vogue. We need to take advantage of that. Some states are even moving towards having teacher licensure in computer science and taking efforts to integrate coding more across the curriculum. And many of us here in this room are actively working to get more data investigations, data science, and computational thinking into the classrooms. So shoulda and coulda, yes, we're doing it. In some classrooms, we are getting kids engaged and excited using bigger data, and it is wonderful to see. So woulda, what are some of the conditions to make this happen? We need resources, and we need the teachers to understand how to use them. We need those data-intensive activities that have meaningful opportunities for the students with real data that they care about. We need computational and visual tools that are easy for the students to use and that can take them into future career pathways. And we need professional development at a large scale. So those of you that know me know I might know something about that. The last couple years, I've been doing MOOCs on teaching statistics and had people engaged across the world, educators and teachers, thinking about how to teach statistics in new ways, using real data, using messy data, using easy-to-use tools. And these teachers are really thinking hard about changing their practices, and they have given us evidence of how they have changed their practices. So we're making a difference. So shoulda, coulda, woulda, but what ain't there? All right, let's evaluate some evidence, and I'm going to pick on high school and AP statistics here for a moment. So meaningful data investigations ain't there. If you have walked into most math classrooms or looked at most math curricula that are being used in high schools, it sucks, okay? There's maybe 1 to 2 variables. There's maybe a context, usually about test scores. Okay, they're small data sets. They're asked to graph by hand or the graphing calculator, and they're taught these rules for mean or median or how to determine what something is an outlier. Okay, so what about bigger data and investigations in AP statistics? So I did a survey this past year of AP statistics teachers. So the survey says it ain't in AP statistics either. It ain't in AP statistics either. All right, we asked these teachers about characteristics of the data that they put in front of their students. Well, we're doing a good job, sort of, about most or all of the time they use real-world data. 25% of our teachers are saying that they don't use real data most or all of the time. Okay, 70%, only a few times do they actually have students collect data. And then thinking about the number of cases or variables, hardly at all are they using any kind of data sets that look real. And multiple types of data, they don't use data sets that have categorical and quantitative variables in them. So when we did interviews with these AP statistics, a sample of these AP statistics teachers afterwards, they just say there ain't room in AP statistics to do big data or to use technology outside of the graphing calculator. So how many of you have used a graphing calculator recently to do statistics or data science? Why is it still in AP statistics? So we need to invest together in the shoulda, coulda, wouldas and get rid of those ain'ts.
Thank you. Next up will be Iddo Gall from the University of Haifa.
Thank you.
Thank you.
Hello, everybody. Thanks for inviting me. Came a long way. Must be a great expert if I came a long way. One of the few international people here. So I've been an advocate of statistical literacy for many years, and I would like to address the theme of the conference from that perspective, evaluating evidence. We all know what evidence is, but what is evaluating? Evaluation comes from the root value. Value means that you appreciate something based on the context in which things appear. You apply external considerations to judge the quality and the meaning of things. And I would argue that we've been paying way too much attention to evidence and way too little attention to evaluation when we teach statistics. And we heard some of the examples here. Even the Gaze report, a great report, but it talks about real data. The questions that we are trying to answer with data do not come from real data, they come from the real world. So there is a big difference between real data and contextualizing instruction. The Gaze report doesn't have almost any reference to contexts and to the problems which bother society or bother industry and from which we draw the data that we analyze. And we just heard from Hollylynne that many of the teachers are using data that they generate themselves based on their own students and so on. So we have a big gap there. So to show that I can also do some graphing activities here, okay, so this is the theme. Hey. So we've been paying, I think, too much attention to getting data, processing data, computing data, displaying data, analyzing, and so on and so forth, and to technical interpretation of results. All too often, I get students who learn statistics and come to research seminars that I administer who are very excited because they got a positive correlation and they don't understand how to put it in words and how to explain what it means and how it relates to the actual meaning of the variables that they are measuring. They just think that every positive correlation that is significant means that things go higher all the time, linearly, monotonously, and so on and so forth. So we have a lot of problems with students not understanding the meaning of the statistics that they actually generate. And I would say that we need to pay more attention to the values of the people who generate the data, the value of the data for the people who need to make decisions and understand how we can use the data to answer real-world questions. What is the purpose of the data that we collect? What are the users and what are the problems that they are trying to solve with the data? And this is usually not in the textbooks. The teachers have to bring it in. They need to bring examples, and most of the teachers are not attentive to this. They may not know enough about it, and so on and so forth. And so I think that we need to teach 30% less processing of evidence and 30% more evaluating evidence and understanding where it comes from and what it serves. And I think in this way we can also deal with motivation and sense of purpose much better than by just being excited about spiffy web applications and things like this. And so I want to make a plug for something that most of you may not be aware of. And this is how do we teach meaningful and important statistics. So Gaze right now is leading the way, paving the road in the United States, but I'm part of a European group that has developed a report from a project called ProCivicStat. This is a collaboration of 6 universities in 5 countries. And we have a whole different set of recommendations regarding what needs to be emphasized in statistics education. And there are other voices out there in the world, in addition to just the ideas that come through GAZE and the community that it represents. And so I encourage you to go and look at the call for action of the ProCivic project, which is on the website of the International Association for Statistical Education. Just go into the International Statistical Literacy Project website and look for our materials, and you will see other kinds of ideas about what needs to be emphasized and why it needs to be emphasized, a lot of resources and so on and so forth. And I think that we need to find a balance point, otherwise we are going to emphasize even more processing of quantitative data. The emphasis on data science is taking us further into algorithmic thinking and black box models and so on, and we need to balance it with remembering why we collect the data and what are the problems in the world that they need to answer. Thank you.
Thank you. Next up will be Jessica Utts. I learned recently that one of Jessica's distinctions is she was the first woman to earn a PhD in the Department of Statistics at Pennsylvania State University.
Don't start yet. Don't start it yet. I'm gonna go to view full screen mode. Okay. Oops. Did I just screw it up?
I probably need to duplicate that.
Okay. Should we go back to not full screen mode?
It's gonna work, isn't it? There we go.
Okay, there's my 5 minutes. Hopefully not. I want to start by, I don't think I need this because I'm going to be here. So I want to start by saying that I don't want to insult your intelligence by thinking that you don't already understand the statistical ideas that I'm going to talk about here. I expect you do. But since this is a conference on teaching statistics, I'm hoping that the way I'm presenting the idea of the paradox I'm going to show you is something that you can use to convince people who don't already understand these statistical ideas. So what I really want to talk about is, not that, what we mean by replicating research findings. You hear a lot about that right now, and the sort of controversy and the crisis, supposedly, in scientific fields because we're not replicating. And as I was preparing this, it came across my desk that there's a new National Academy of Sciences report just out on reproducibility and replication. And it defines replication as obtaining consistent results across studies aimed at answering the same scientific questions, each of which has obtained its own data. So that's what we mean by replication. But then one of the summary points is one type of scientific research tool, statistical inference, has an outsized role in replicability discussions due to the frequent misuse of statistics and the use of a p-value threshold for determining statistical significance. And that's the point that I've been trying to make for a very long time. And Alan sort of gave you his age. You can get some clue of mine here. So this is a t-shirt someone made for me in 1988 for a conference. No using p less than or equal to 0.05. And I don't have time to tell you the backstory, but if you want an icebreaker to introduce yourself to me, I'll be happy to tell you the story behind that. So what I'm going to argue for is using effect sizes to discuss replicability. And if you're not familiar with effect sizes, basically an effect size is the distance between a null hypothesis value and the true population mean for a one sample situation in terms of number of standard deviations. Or for two samples, the difference between the two population means in terms of number of standard deviations. And just as an example, for male and female heights, the averages are about 5 inches apart. And the standard deviation in each group is about 2.5 inches. So that's an effect size of 2. And effect sizes that large are supposedly visible to the naked eye. And I think we would all say that we can notice that males in general are taller than females. I collected some data on my own students, but here you have it, on whether women students these days are taller than their mothers. And I found an average difference of 1.3 inches with a standard deviation of 2.6 inches, which very nicely works out mathematically or arithmetically to an effect size of 0.5 if we're testing whether or not there is a difference in current students' heights and their mothers' heights. And that's actually considered to be a moderate effect. And moderate effects supposedly are not visible to the naked eye, but you can detect them with statistics. And in this case, you can see that the t-statistic comes out really large, 4.8, so the p-value is essentially 0 for the hypothesis that students are not, on average, taller than their mothers. But I wanted to point out the effect size and how it relates to the t statistic here. So in red is the effect size, and in red again with the t statistic is the effect size. And so you can see that even if you replicate studies that have identical effect sizes, you're going to get vastly different p-values and t statistics completely based on the sample size. And that's where people have gone wrong in trying to define replication. So here's the paradox that I want to talk about. A researcher conducts a test with a sample of size 100, gets a t-statistic of 2.5, p-value of 0.014, and gets very excited because it's statistically significant and is going to get published. But the researcher knows you have to replicate, so just to be sure, but it's already shown effect, so the researcher's only going to collect 25 this time around for the second study. Uh-oh, the effect's gone away. Now the test statistic's only 1.25, p-value is 0.22. It has not replicated the result. Darn. So now the researcher says, well, I'm going to try to salvage this. I'll combine the data. Combines the data, gets a t of 2.795, p-value of 0.006. So now it's even stronger than the original study. So the paradox here is that the second study alone did not replicate the finding, but when combined with the first study, the effect seems even stronger than the first study. And people who aren't statisticians don't get what's going on here. So clearly what's going on is that defining replication as getting statistical significance each time or on the basis of p-values makes absolutely no sense. And yet it's what most people do. So you're the ones that need to explain this to them, what's going on here. In both studies, the effect size was 0.25. So the test statistic and p-value are completely dependent on the sample size. Okay, so that is the paradox, and that's the explanation for it, because the test statistic is just always square root of n times the effect size. So in conclusion, I think effect sizes are what we should be looking at, because unlike p-values, they don't depend on the sample size. They're a measure of the true effect or the difference in a population, so we can look at practical importance. And finally, replication should not be defined as getting approximately the same effect, should be defined as getting approximately the same effect size, not getting approximately the same p-value or getting statistical significance every time, which is what researchers out there think it is. So, okay, that's it.
Thank you. Next up will be Larry Lesser from the University of Texas, El Paso. Larry also has a PDF, so. Does it fit or does it not fit? We need to shrink the screen.
Yeah, how does that work? There we go. That should do it. This works, right? Okay. I don't know why, but a lot of people keep asking me if I'm going to be singing today. So I'll just sing one line as Bradley Cooper to kind of summarize the theme here. Tell me something, friends. Are you tired of how we teach significance? Okay. But my real thank you. My talk is sort of a stat ed slant and kind of like from an individual instructor view. And for a 5-minute talk, less is more. So I asked myself, what one change in my 3 decades in the classroom has had the most bang for the buck for my teaching and students' learning? And I mean throughout a course, beyond testing a strategy for one bit of content at a time, though I've done some of that. And I've also done randomized experiments, but I agree with my friend John Holcomb that it's not always relevant, possible, or even ethical to do them in teaching. And I wanted to focus on real-time evaluation because I agree with Dilly and William that the most important assessment happens during the learning when there's still time to do something with the information. That assessment, of course, is called not summative, but excellent. See, we just did an assessment right there. And so for me, for my journey, my cool tool has been a piece of paper folded in fourths, the ABCD card, okay? And it's multiple choice, of course, but you still can and must ask good questions. And ask good questions aren't just recall, they follow the Gay's recommendation that it's better to aim for conceptual understanding, right? ABC. Gaze itself has examples of writing and revising items, and online, there's many examples there. There's also online collections of clicker questions by people like Derek Bruff. You can also get ideas from items in the Artist collection, and Artist, of course, is one of many research resources on CAUSEWeb. But half of my questions are actually unplanned in class, orally improvised in the moment, such as we've just finished discussing a data set, and I'll just tack on a what-if question. What if I delete the outlier? Then R would A increase, B decrease, C stay the same, D? No idea. And doing things like that creates an immediacy with students because you're responsive in real time. They know you're going beyond what you sort of had scripted. But whatever the question is, you can see it's easy to pan the room of any size and tell that, in this case, most people voted A. And students can give you feedback not just on how they're understanding the concepts. Sometimes I let them vote to say, choose the next the context for the next example, to again, personalize and tailor the experience. And without even interrupting you, they can use these cards to give you feedback on your pacing. Like if the students start flashing a lot of green, that means speed up, don't belabor this, right? Or yellow, slow down, careful, you're starting to lose us. Red, stop, abort, whoa, back up, right? And so I learned about this 9 years ago from the University of Arizona's Ed Prather. And unlike most professional development, I started using it right away. In the very next week when this class has started, I was teaching a stat literacy class with Jessica's wonderful textbook. And it actually changed my mindset because it inspired me to live up to making every single class interactive and engaging, because I don't have songs for everything. I got to rely on something else. And to assess every student's understanding on every question, because normally we throw a question open to the room, the same 4 volunteers answer 90% of the questions. But here you pan the room and you're getting everybody involved on every question. And you empower the students to learn from each other. If it's a split vote, I don't just tell them the correct answer was B. I say, turn to your neighbor, try to convince each other you're right, go. And then 30 seconds later, we re-vote. I haven't said anything. And the distribution of answers is always closer to the correct answer. It's really neat when that happens, because it always does. So let's assess this assessment tool. There are studies on clickers, like the randomized experiment and ties, if not on ABCD cards, but it's really not about the type of personal response system. It's about the underlying active learning that they facilitate. And there's a lot of support for active learning, huge meta-analysis there. And we know that Gaze recommends fostering active learning because active beats canned, right? And so from my gut and from the literature, I was pretty confident I was doing a good thing, but I still wanted data on my students, even if it was self-report data. So after I'd been doing this for about 3 months, I step out of the room, I have the director of my university's teaching center give a survey asking 3 things, asking about student engagement, feedback on student learning, and feedback on instructor teaching. And I was stunned. 100% of the quantitative and qualitative answers were positive. Like, that never happens, especially the first time you try something new. Like, you know, and that's never happened since. And so, you know, and I still use it. It's been consistent with comments that people make in my end of course ratings. You know, it's always in the top 2. Songs is probably the other thing. And so the main thing, I mean, that tool, this is the tool that was transformative for me. But it'll probably be something else for you, and that's fine. The point is to always be curious about what is the thing that's going to improve your teaching throughout a course. But remember to put those ideas to the test, because assessment beats just conjecturing about it. And so as you have a wonderful USCOTS, look for that one cool thing that you're going to try this fall and plan to assess it. And you'll find there's lots of great ideas to pick from here, because USCOTS is the year's absolute best conference. Okay, thank you. Thanks in no small part to Alan's brilliant chairing. There's another ABC. So, sorry, JSM. And so I thank you and leave you to read some UTEP fun facts. Thank you.
Thanks very much. Next up is Michael Posner from Villanova University. And we're back to PowerPoint.
Great. Thanks, Alan, for inviting me to do this. So I've been doing a lot of work in the last couple of years in data science, and I thought I would share a little bit. The ASA is working with the ACM. We have 2 folks going to the SIGC meetings, to their professional conferences. We have a session at JSM this year where we're bringing statisticians and computer scientists to each other's venues to talk about what we can learn from each other. So that's what I wanted to talk a little bit about today. So what is data science? I have an hour, right? No, I can't do that. All right, you guys know this. Let's do assessment. With big data comes Venn diagrams, right? So the original one, hacking, computer science skills, math and stat knowledge, and subject matter expertise. That's what most people agree as what formed data science. Everyone wants to get on the bandwagon, so the graphic designers thought they could come together and figure out how they can become better paid people in the world. And there's one more recent one that really looks at it as a superset and said data science is all of this together. And then they kind of realized that no one's an expert of all of them, so we're kind of searching for that elusive unicorn in the middle. And I think that one has some truth as well. So I thought I would give you a little anecdote. So imagine you're the CEO of a company. You want to find out what your return on investment is going to be next year. That's what ROI is, right? So you go to your computer scientist and you say, can you please estimate for me what the ROI is going to be next year? And they come back and they get the answer in about an hour. They're really good with that stuff, right? And they say the return on investment next year will be 3%. Okay? That's scenario 1. Scenario 2 is you send out the statistician to do the same job. Statistician takes a little bit longer to process the data because maybe it had some JSON in there and couldn't figure out that tree structure that was going on, right? And then they come back and say, Alan Rossman told me to ask good questions, so I'd like to know, should I be doing a non-parametric model or Bayesian inference? And eventually they come back to you and says, well, if all the assumptions you told me are true, I'm 95% confident that the population ROI is somewhere between 2.4 and 3.6%. Who do you want to hire? This is a challenge. In speaking with my colleague from computer science, we talked about the data life cycle. If I were to ask you, where in this life cycle does the statistician's role lie? I think you can argue that it's almost all of them. We don't really do cybersecurity. Storage, maybe not. All right? When I asked my computer science colleagues what role it was, we were talking about a curriculum for an intro data science class. What they told me was, you can do the analysis. Maybe we can share the visualization, right? That's what they thought of as our discipline. When I gave them all of the important topics that I thought were crucial for students to understand as statistical thinking ideas, twice they simplified that to basic statistics. That was painful. USCOTS is one of my favorite conferences. We've got great sponsors. I looked up these numbers. I hope it's not supposed to be private. Premier sponsorship comes at $4,000 for USCOTS. We got, what, about 500 people here? Fantastic conference. I went to SIGC. That's the Computer Science Educators Conference. They have 1,500 people there. Their sponsors require them to pay $25,000 for platinum sponsorship. I couldn't even fit the silver and bronze sponsors on here, because they have a lot more money, they have a lot more fellowships, they have a lot more scholarships that they're giving for people for doing this, right? When we have DataFest, great opportunity for statisticians, we offer bragging rights. They offer $10,000. That's why we're losing the battle. But I'd like to change this challenge into an opportunity. And I heard this expression recently that I really liked. Know what you know and know what you don't know. We do a pretty good job with descriptive statistics and multivariable thinking. Some of us need a refresher or new training on programming skills so we can keep pace with the data that's out there. There's a couple other things that I like. The idea of building up your analysis. Start simple with a univariate analysis. Understand what the distributions look like, what the data look like. Are there missing values or not in your data? How do we handle outliers? How should we put these into models in the future? And then the one and done fallacy, students who think, well, if I figure out this is a one sample t-test, I'm done. That's all I have to do for the entire project. And given that they're in chapter 3 of the course, they have a good idea of which one's appropriate. All right, so things are not one and done in the real world. Know what you don't know. We do a good job with uncertainty and inference. We need to do a better job in our intro courses about understanding bias. So not just missing variables, confounders, missing cases, the entire person's not there, sampling bias maybe, missing values, why did a person not respond? We need to be thinking about all of those. The computer scientists liked this when I said it's also about how you process the data. The choices you make in processing can introduce bias as well. And then causal inference and causation. Subject matter expertise, that's the other one we should leave up to the subject matter experts as well. The last one I'd like to add to this, though, was also what inspired me from USCOTS. Hillary Parker spoke about design principles in statistics. If what you are doing does not leave someone with a new learning, a new insight, an aha moment after you've presented to them, it's not useful, even if it's the best statistical model ever. My advisor from Boston University testified in 2000 in Florida about the recount. And she said the biggest mistake she made was talking like a statistician on the stand instead of talking more definitively about what she thinks was the case. All right, so that communication is really important, and we have to realize that simple is sometimes the best. So in summary, at the USCOTS, we should think about how to promote a quality statistics education for our students, but we should also think about how do we do that for ourselves, as well as how we do that for our peers in other disciplines. Thank you.
Thank you. The last of the 5-minute speakers, and I do want to point out I have a few more things to say after Bill's 5 minutes, but the last of the 5-minute speakers is William Bill Finzer. Let me get his PowerPoint up. You want the, sure. You might not need it. Yeah. You want that mic or this mic?
I'll take that one.
All right. Go ahead. Oops. Yeah.
So this is going to be introspection. I'm fond of saying that I wish for K-12 students with respect to data science is that they have multiple experiences of data immersion. But what does that mean? With your forbearance, I'll try to describe what it's like for me. I know I get a lot of pleasure from data immersion. I believe that if students could have a data immersion experience at least once each year of their schooling, they would come to expect that data be a part of every learning experience. They would acquire confidence in their abilities as data problem solvers and come to enjoy exploring data as a way of experiencing the world. And of course, data are part of the evidence for any claim, and immersing yourself in the data helps with, or may be essential to, evaluating that evidence. So here we go with apologies for all idiosyncrasies, artifice, and the rough-hewn video. It takes time to get to know a data set. The more cases and the more attributes there are, the longer it takes. And the more interesting the data are, the more time you want to spend getting to know them. The data set starts as a stranger you're not sure how to approach. You may want to come in obliquely, learning first about its origins, its reason for being. You want to know more about the context of the data, scientific, business, governmental, or something else. Or you may want to fearlessly walk right up and say, "Hello, show me your stuff." Perhaps you come to the data set with a question in mind. Does it seem to have potential to answer that question, or should you get out while the getting's good? Typically, graphs, maps, tables are your helpers, allowing you to quickly learn important things. This attribute has numeric values lying in a skew distribution. It has dollars for units and extreme outliers. This attribute has only a few categorical values, and most of them belonging to a single category. This boundary attribute suggests you plot it on a map. But what do the points in one of the graphs represent? What is the case? Do the cases represent geographic entities that will show up nicely on a map? Is each case simple, representing a single entity or event? Or is each case a combination of things that should be pulled apart somehow? Perhaps there is a natural hierarchy in the data set by which cases of one kind belong to cases of another kind. Do the data need cleaning? And if so, how much work will that take? Will you need to document the cleaning process? And if so, will it be fun or tedious? Manual or automated? will the result be worth the effort? All along, you're getting a sense of the stories these data have to tell and how these stories relate to the question that drew you to the data in the first place. The data start to make sense as you become able to hold some of the relationships between variables in your mind. You feel surrounded by the data. You can reach out and touch it with your mouse and your keyboard, swapping, adding, removing variables, selecting portions of the data, zooming into dense clusters of points, adjusting colors to bring out features. You experience data as something malleable. You've been exploring, taking note of features and relationships you find along the way to come back to and investigate more deeply. Perhaps you think you might have made a discovery or several, some things you want to show others. You go back to near the beginning to recreate your path, to document it so that others can follow where you've been. You've been immersed in the data so that for a few minutes, hours, or days, you climb out, give yourself a good shake, and reflect on where you've been and what you've done. So it's something like that for me. What is data immersion for you and for students? Is it something we want to strive for in data science at the pre-college level? Thank you.